16.8 Intensity of sound waves. In this session, we will explore the fundamental concepts of sound intensity. Our outline includes defining what sound intensity is and examining the rate of energy transfer in periodic sound waves. We will also discuss how intensity varies when dealing with a point source and introduce the decibel scale used for measuring sound levels. Finally, we will look at the limits of human hearing and how our ears respond to different frequencies. Sound waves are not just vibrations. They are a means of transporting energy through a medium. To understand this, imagine a piston moving in simple harmonic motion against a gas element. As the piston moves, it does work on the gas. The instantaneous power, or the rate of this work, is found by taking the dot product of the force vector and the velocity vector. In a fluid, this relates to the change in pressure times the area and the rate of change of displacement over time. Mathematically, the instantaneous power is equal to the density of the medium times the wave speed times the angular frequency squared times the area times the square of the maximum displacement, all multiplied by the sine squared of the quantity wave number times position minus angular frequency times time. While instantaneous power fluctuates, we are often more interested in the average power over one full oscillation period. The average power is calculated as 1/2 times the density of the medium, times the area, times the angular frequency squared, times the maximum displacement squared, times the wave speed. From this, we define intensity as the average power per unit area, where the area is perpendicular to the direction the wave is traveling. For a periodic sound wave, the intensity is 1/2 times the density, times the wave speed, times the quantity angular frequency, times maximum displacement squared. This shows that intensity is directly related to how much energy is passing through a specific space every second. Intensity can also be expressed in terms of pressure, which is often more practical because the density of a gas is easier to measure than its bulk modulus. We know that the maximum pressure change is equal to the density times the wave speed times the angular frequency times the maximum displacement. By substituting this relationship, we find that intensity is equal to the square of the maximum pressure change divided by the quantity 2 times the density times the wave speed. This formula highlights that the intensity of a sound wave is proportional to the square of its pressure amplitude. When a sound source is very small, we model it as a point source that emits sound equally in all directions. This creates spherical waves. We visualize these using wave fronts, which are surfaces where the wave has a constant phase, such as the crests of the waves. The distance between these adjacent wave fronts is the wavelength. We also use rays, which are radial lines pointing outward from the source. These rays are always perpendicular to the wave fronts and indicate the direction the energy is traveling. As a spherical wave travels away from a point source, the energy it carries spreads out over an ever-increasing area. The average power emitted by the source is distributed over the surface area of a sphere, which is 4 times pi times the radius squared. Consequently, the intensity at any distance r is the average power divided by 4 pi r squared. This relationship is known as the inverse square law. It tells us that if you double your distance from a sound source, the intensity of the sound will decrease to 1/4 of its original value. The human ear is an incredibly sensitive instrument. The threshold of hearing, which is the faintest sound we can detect at 1000 Hz, has an intensity of approximately 1 × 10 to the -12th watts per meter squared. On the other end, the threshold of pain is about 1 watt per meter squared. In standard air conditions, the pressure change at the threshold of hearing is only about 28.7 micropascals. This corresponds to a maximum displacement of the air molecules of about 11 picometers. To put that in perspective, our ears can detect movements smaller than the size of a single atom. Because the human ear can detect such a massive range of intensities, we use a logarithmic scale to measure sound levels. The sound level, represented by the Greek letter beta, is defined as 10 times the logarithm of the ratio of the intensity to a reference intensity. This reference intensity is set at the threshold of hearing, or 1 times 10 to the negative 12th watts per meter squared. We measure these sound levels in decibels. On this scale, an intensity increase by a factor of 10 adds 10 decibels to the sound level, while doubling the intensity increases the sound level by approximately 3 decibels. To give you a sense of the decibel scale, let us look at some typical sound levels. A nearby jet airplane can reach 150 decibels, while a rock concert or a siren is around 120 decibels, which is the threshold of pain. Busy traffic usually sits at 80 decibels, and normal conversation is about 60 decibels. A soft whisper is around 30 decibels, and the threshold of hearing is defined as 0 decibels. It is important to note that for any environment exceeding 90 decibels, the use of earplugs is highly recommended to prevent permanent hearing damage. It is important to distinguish between the physical measurement of sound and the psychological perception of it. Loudness is a subjective response that depends on both the intensity and the frequency of the sound. As a general rule of thumb, for a sound to be perceived as twice as loud, the sound level must increase by about 10 decibels. This means the actual physical intensity of the sound must increase by a factor of 10 to achieve a perceived doubling of loudness. This graph illustrates the frequency response of human hearing. We are generally sensitive to frequencies between 20 Hz and 20,000 Hz. Frequencies below this range are called infrasonic, and those above are ultrasonic. The white area represents the range of normal hearing. Notice that the threshold of hearing curve dips significantly between 1,000 and 5,000 Hz, meaning we are most sensitive in that range. While the threshold of hearing varies quite a bit with frequency, the threshold of pain remains relatively constant across the entire audible spectrum. In summary, sound intensity is the power per unit area and is proportional to the squares of both the displacement amplitude and the angular frequency. For a point source, intensity follows the inverse square law, decreasing as the square of the distance increases. We use the decibel scale to compress the wide range of detectable intensities into a manageable set of numbers. Finally, we must remember that perceived loudness is a subjective experience that is influenced by both the physical sound level and the frequency of the wave. To wrap up, let us consider 2 review questions. First, if you move to a distance that is 3 times further away from a point source of sound, by what factor does the intensity change? Think about the inverse square law here. Second, if a sound source has a sound level of 70 decibels and the intensity is increased by a factor of 100, what is the new sound level in decibels? Consider how a factor of 100 change in intensity relates to a change on the logarithmic decibel scale.